Let me start the session. It's really my pleasure to introduce Dr. Thomas Bligaard from SLAC National Accelerator Laboratory and Sunshine Center in California. Thomas has been professor in the Department of Physics at the Denmark Technical University from 2006 to 2011, and then since 2011 he has moved to California at SLAC and Suncat, where he's also deputy director for theory at Suncat. His expertise is in the calculation of physical chemistry, chemical properties of surfaces, heterogeneous catalysis and processes, and the properties of transition metal in analysis. And today we will discuss how to combine machine learning elements with high-throughput simulations. Thomas, please.
Well, thank you very much. I am extremely happy to be here in Lausanne with you for this workshop. Unfortunately, I'm only here today, so but we can chat more at the poster session here later in the evening. So what we're working on is basically trying to search for new catalysts in a theory-driven way. So integrating theoretical simulations with synthesis, characterization, and testing methods for catalyst discovery, and trying to sort of integrate all these different aspects with lots of experimental researchers at Stanford and SLAC. And more, I believe that this integration of these different fields is seemingly becoming sort of the creation of large databases and machine learning methods to make models based on the data in those databases. And I think this AiiDA infrastructure that you're learning about today is really at the forefront of establishing sort of a foundation for doing this in a very organized way, where you have control of everything that is done in your electronic structure calculation from birth to the final sort of analysis that you're doing of your simulations. And so I'm extremely enthusiastic about this AiiDA code that you guys are, or some of you guys are developing, and I really hope that you get a lot out of this meeting. So in catalyst discovery is something that we really need in order, for example, to address some of the environmental problems that we are facing. For example, if we want to create some kinds of transportation fuels based on renewable sources, basically it comes back to creating those fuels from sunlight. And however you want to do that, through biomass conversion, through using electricity from the sunlight to create these, or using photoelectrochemical processes, all of these different procedures require new and improved catalysts to make some of these fuels. And so it's a field where we really need not just sort of another few catalysts to run a couple of different processes, but we need to drastically change our ability to devise novel catalytic materials to run processes under different reaction conditions than we are used to. And those catalysts, because we are addressing a problem that is enormous, it's a huge conversion of energy that you need in order to create something that can substitute, say, hydrocarbons from fossil resources in order to make fuels. Then you need to make these catalysts of earth-abundant materials that are cheap, so you can make fuels for hundreds of millions of cars, right? So trying to attack that from a theoretical point of view would be elegant in the sense that the number of DFT calculations that we can do over time grows exponentially according to Moore's law increase in the computer power, right? But sort of our fundamental problem in doing that at the outset is that if you want to look even at very simple reactions, here the conversion of natural gas or methane to syngas, which is something you can use to synthesize whatever hydrocarbon you like in the end. The way we would normally approach that is to calculate adsorption and barriers for these different elementary processes that goes into this overall process on some surfaces. For example, here, close-packed nickel surface or a stepped nickel surface. And you see that the results you get are sort of very dependent on the specific facet of a given metal that you have. And in order to really say something about the activity of this surface for a catalytic reaction, you really need to know everything that's going on here and put it into a microkinetic model of some sort. You need to know all the adsorption energies and all the barriers to sort of finally get a result. And that means here, just in this very simple reaction, there's 16 dimensions that change when you look at different facets of materials or different metals in the periodic table, right? So it's a large dimensional problem to begin with, and there's just basically too much complexity to really understand what's going on when you're changing reaction conditions, materials, surfaces, etc. Now, fortunately, sort of over the past decade, a very structured approach has been implemented to sort of mitigate some of this problem through so-called scaling relations, where for example, adsorption energies of some species scale linearly with adsorption energies of other species on a surface. That also goes for transition state energies as a function of adsorption energies or dissociation energies here for very many different surface reactions on transition metal and alloys. Follow these sort of approximate linear relations. There's some uncertainty, and it's of course a big question, is there too much uncertainty to actually use these for anything? Or is the uncertainty under control enough that this is actually useful, right? But it basically means that if you employ these linear relations, you can correlate all these different adsorption energies and barriers with sort of very few. So you have a physical model for a dimensionality reduction of the problem. And our original 16 parameters here, we would typically scale down to 2 parameters because carbon adsorption energy and oxygen adsorption energy, for example, does not correlate very well with each other on the surface of these metals. So, but you can reduce this to perhaps a 2-dimensional space and then try and address sort of optimization of this problem in this low-dimensional space. And if we look at the kinetics here, here's a little bit more reaction steps introduced, but you get such a microkinetic model for the activity as a function of these descriptors, carbon and oxygen adsorption energy, and you now get sort of an activity out as a function of these 2 descriptors, and you can see where sort of the elemental metals is on a map like that. And now, using that, if you sort of assume that this still works if you go to alloy materials, you can now calculate just these descriptor values for a bunch of different alloys and sort of see, is there something that is supposed to be active on top of the volcano that we could go out and test? Or you can combine this with sort of what you would typically do in a more advanced approach. If you're really sort of interested in making some of these, you want to combine it with lots of other criteria that the material needs to fulfill in order to see whether it could be a technical catalyst, right? Is it stable under reaction conditions, or does the alloy that you're looking at sort of segregate into the pure metals? Or does it turn into an oxide? Or is it too expensive? Or is it selective, for example, for the reaction you're looking at? So you typically have such sort of different criteria to fulfill, and each one of them can, if it's not fulfilled, it can sort of make the catalyst unuseful, right? If you think, wow, this is a very good catalyst, it just only lasts 10 seconds, then it's gone, right? Then it's not a good catalyst anyway. And so typically you have many different sort of constraints that you need to apply at the same time to actually find something that's a useful new material. What that means is, say, if at each level here it's only 1 out of 10 that actually is stable, that actually doesn't turn into an oxide, that actually is active, etc. Well, then, of course, you need to then carry out very many simulations in order to actually have a material at the end, right? Because if you start with here 10,000, then after you go through one step, you have 1,000, you go through another step, you have 100, you go through another, you have 10, etc., right? And sort of real materials that you're designing in industry need to fulfill many of these different criteria at the same time. And so what we really do need is sort of massive databases of materials properties where we can go in and harvest information about these properties for lots of different materials properties that we want to know for them, right? And that's sort of one of the aspects where AiiDA comes into play, and where you can really sort of save your data in a way that other people can go in and reuse it for in a way that you didn't think about at the time that you did the calculation, right? And I think as we're moving forward in this field, we really have to share our simulations with each other, allow other people to harvest information that we were not thinking about at the time that we did the simulation, right? And that will accelerate the discovery of novel materials for all of us. So there's sort of various reasons that this sort of type of trend study of the activity is very general. You can sort of analyze it in terms of the Hammer-Nørskov model, where some adsorbate energy level interacts with a SP band and a D band of a transition metal, and you'll get that the adsorption energy correlates with the D band center. And if that goes both for, say, the initial state and the final states of a reaction, or if it goes for the transition state and the final state of a reaction, right, then you get these linear energy correlations. And they're really very omnipresent in the field of surface chemistry. And basically every reaction we look at, we end up with sort of plots like that. There's sort of slight complications on top of this when you go into specific reactions and try to understand trends. For example, if you look at unsaturated hydrocarbons, you can have that these lines sort of have a tendency to have different slopes in different regimes, and one can try and understand sort of details about that. If you go to, say, other compounds than transition metals, this sort of fundamental correlation seems to hold pretty well, though. Here, NH and NH2 correlated with the nitrogen adsorption energy over different nitride surfaces. OH correlated with oxygen over different oxide surfaces, and SH groups correlated with sulfur adsorption over different sulfide surfaces. So it's sort of very, I mean, even if you don't have sort of the underlying physical model, like the D-band model, to which you can't really apply on these types of materials, it seems sort of a fundamental rule that there are these underlying correlations here for transition states, for dissociation of various molecules over oxide materials. So it's really omnipresent, right? The question is, of course, is it useful enough? Are there uncertainties that are big enough that sort of the actual result that you want to find in the end drowns in the uncertainty of your simulation? Now, sort of one way that has inspired us to sort of get beyond the linear scaling relations is, well, we have sort of a little web app that one can look at reaction energies and barriers for some of the calculations that we have done in the group. What would really be nice was that if you, well, what turns out is that typically, you know, you either knew you had this reaction energy and barrier, and then you can go in and look it up, and that's fine. But very often you're sort of looking for something that's not in there, right? That just sort of tends to be, as you're moving on and looking at other reactions, you're looking for things that you haven't calculated, right? So what would be very nice is that if this little gadget could sort of give us the answer to sort of any reaction that we were interested in for any reaction on any facet of any surface, right? And sort of the hope that we have is that one can apply machine learning to do something like that. And here there's very little information to sort of correlate or to use as fingerprints in a machine learning method in this database. There's basically just what is the adsorption or the reaction energy, and what is the barrier, and what is the molecule, and what is the surface, right? There's really nothing to learn on in here. But even with that very shallow set of data to try and define a fingerprint, if you just put that into a kernel-rich regression, you can sort of see here a linear correlation between what the machine learning model says and what the full DFT result is for the reaction energy in this case. And there's definitely sort of a correlation. It's not perfect, maybe not quite as good as the linear scaling relations, right? But it's sort of there. It certainly means that if you're looking for something that's down here, you can sort of look at some of these materials and you can avoid looking at the rest, right? And that is very often what you need if you have sort of a materials property where you just need to find sort of a few material that could be of interest and you don't want to look at a whole lot of material. But with an infrastructure like AiiDA, when you have that, right, then you automatically sort of save not just sort of what you were interested in at the time that you did your simulation, right? You save potentially all the details about the simulation in a way that you can get back and figure out, oh, maybe we can use these metadata things to put into the fingerprint to learn something from. And I think that's one of the great advantages of an infrastructure like that, that you can very naturally use it to create fingerprints for machine learning methods later on. And so I think that is one of the aspects where it will become extremely useful. Now, if we sort of want to treat this uncertainty that we have in basic descriptor-based catalysis as it is, you sort of want to figure out what are the error sources, what are the uncertainties that these error sources introduce, and what is the sensitivity of the scientific conclusions that you are trying to make on the uncertainties that are introduced, right? And there's sort of lots of different things that could be improved. And what I'll talk about today is especially looking at sort of structural and mechanistic assumptions that you have in your sort of reaction setup, that you always start by sort of assuming, oh, let's assume that it's this set of elementary reactions that we're going through over this facet of this surface. And then we're doing that in great detail, and it costs a lot of DFT power to do these simulations, right? But it's all a waste if you actually sort of are not looking at the real reactions that are actually going on, or if it's not the real facet of where the catalysis would really happen on this material under reaction conditions, right? And then the uncertainty in our electronic structure theory basically always comes from sort of, or to a large extent, from the exchange correlation treatment in our simulations. So that is a good place to start in terms of looking at the uncertainty. And so in sort of building density functionals, there's this Purdue's ladder of, you can sort of mix in more and more degrees of freedom in your functional and try to get it to be better and better. Purdue, he would sort of argue for putting exact constraints in, and as you're doing this, right, we're taking sort of the more sort of chemistry community approach of trying to fit these functionals with sort of expanding model spaces and trying to fit the DFT functional to sort of well-defined data sets calculated maybe at a sort of high-quality data from quantum chemistry simulations, or sort of experimental values that we would like to reproduce with the functional. And then we use sort of machine learning techniques to make the model selection to sort of fit the model as well as possible, but avoiding overfitting. That is sort of what machine learning does, right? Try to fit a model without overfitting it based on the available information. And particularly, so using Bayesian model selection, you don't just get the best model out. The best model here fitted to the databases we have introduced would be this black line here. This is the exchange enhancement factor as a function of the reduced density gradient. But it gives you a probability for sort of any enhancement factor that you could map here, right? And so as you get further and further away from this enhancement factor, your probability of the model being a reasonable model falls off very fast. And you get sort of an ensemble, and you can simulate these different enhancement factors in such a way that that you choose the spread of this ensemble so that, well, the best one is the one that sort of best possibly fit the data that you wanted to fit, but the ensemble has a spread such that it reproduces the error on the data that you tried to fit. And what this gives is an opportunity to sort of propagate the uncertainty that you can see that you have in a well-defined system to whatever you want to model afterwards by modeling whatever you want to model afterwards with the whole ensemble of these functionals. And then seeing sort of what is the spread of the predictions that you're making when you're using this ensemble of functionals. And if we put that into a model, for example, for ammonia synthesis, here on some steps of some transition metals, then we have here what is the logarithm of the turnover frequency, this is the activity, as a function of the inverse temperature. And that's this line here, which is with sort of the optimal chosen functional, right? And then we have the experimental numbers there up here. And this is the situation we would normally be in, right? We have a theoretical result. We have an experimental result. It sort of correlates, and it's sort of difficult to say whether we really, are we modeling the right thing? Is the experiment and the theory close enough that we can say they agree, or are they too far apart, right? But now having the ensemble, well, you can model sort of many different DFT models from this ensemble of functionals, right? And then you can look at, for example, what is the one standard deviation of the theoretical results? And is the experiments within, say, 1 or 2 standard deviations? So is there some, that tends to suggest whether you're looking at the right thing with your theoretical simulations, right? And so in this case here, it could be that the actual process takes place on stepped facets of these transition metals. And that seems to sort of correlate well with the temperature dependence of the activity and with the apparent effective barrier over these metals. And often when we are modeling catalysis, we are sort of not getting the absolute rates very well. Often here in this case, for example, for ammonia synthesis, they're off by about 2 to 3 orders of magnitude. And we see that the uncertainty here in the activity as modeled by one standard deviation of these different ensembles, different functionals in the ensemble is on the order of 1 to 2 orders of magnitude. However, we also know that we typically sort of get closer to actually predicting differences between different materials. And if we just look at the relative activity compared to iron, then our uncertainties are now significantly smaller. And now, using such an ensemble, we can say, instead of, oh, ruthenium is better than iron, we can say, sort of, what is our confidence in ruthenium being the best of the elemental metals? And in this case, we can say with approximately 20% confidence that ruthenium is the best of the elemental metals for ammonia synthesis. So here, using sort of an underlying machine learning approach, you get an ability to model the uncertainties, and that's very general, right? Machine learning is typically based on, say, Bayesian inference or Bayesian statistics, and it gives you, say, a way to sort of keep the inference that you're doing under control, and in the end give you an uncertainty on the results that you're having, which can be very useful, I think. Now, another example, that is, if we're looking at the sort of structure of which we're doing the catalysis, for example, we have this transition metal surface, and we're now trying to figure out what is the reaction network for going from our reactants. In this case here, it's now syngas conversion. In syngas conversion, you can have extremely complex reactions. This is just to the first level, or so to say, second level, where we have a couple of C2 species. But as your carbon chains grow longer and longer, this network here explodes, and you get hundreds of millions of different elementary reactions that you could be going through, right? So even just going to the level of C2 species, you sort of have a relatively complex reaction network, and you can try and ask, sort of, how do we, using electronic structure theory, model that kind of complexity? If we have to sit down and figure out all the different elementary reactions that could be relevant and calculate with DFT all the reactions and all the adsorbates that goes in and all the NEP calculations for all the barriers, then it is already extremely time-consuming to get to the C2 level here, and getting to the C4 or C5 level or something is totally untractable. And so the question is there a smarter way than sort of by electronic structure simulations mapping out everything and then putting everything into a microkinetic model and then figuring out sort of what was relevant, right? And here I think machine learning is promising in the sense that one use that has been in say, construction engineering is you have these simple models, back-on-the-envelope type models, right? So you, instead of calculating a bridge, is it stable in weather conditions and with certain wind and with people driving on it, etc., doing the simulations on the whole bridge is a very complex task. And you sort of have some back-of-the-envelope estimates that you do along the way as you're designing your bridge, and you can do those very fast. And sort of by doing most of your simulations, sort of these fast back-of-the-envelope simulations, you can speed up the design of a bridge tremendously. That has been used for the past 50 years very widely. The same with machine learning, where instead of calculating these very expensive electronic structure simulations for our large systems with adsorbates and a thick slab of a surface, you can do a lot of predictions, say just if you have a database of energetics calculated from an earlier study, and you fit that to a machine learning model, and this surrogate model you use to make predictions on what is it actually I should be calculating, and then you calculate that instead of calculating everything. And if you have in sort of uncertainty estimates on what you're calculating, you can even say, now what could be relevant to calculate of other things? And that is the approach that we're taking here. So starting out from a sort of a non-relevant database for this specific problem, fitting a surrogate model, and then asking, sort of, what do we think is the correct reaction path that this is taking? And then we'll do some DFT calculations for some of those species and see if our machine learning model was right about the energetics. If it's totally off, then that's not the right reaction pathway anyway. And then what does it suggest now as we have more data to fit a better model, right? And so it means that instead of sort of our normal approach of doing sort of expensive DFT calculations, expensive notched elastic band calculations, and expensive microkinetics in the end, we sort of just run through the whole machinery just using machine learning numbers and try to figure out which adsorption energies and barriers is it that we actually need to calculate. And the only thing that we put in is a very sort of shallow fingerprint here of just describing what is the adsorbate that's sitting on the surface in a sort of simple smiles representation. And typically this representation is relatively long compared to the number of data points we have at the outset. So we reduce that using sort of a linear dimensionality reduction scheme. And in this reduced dimension, we just fit a Gaussian process, which is a very stable machine learning method to try and predict adsorption energies and barriers. And we get energies and barriers out from that model. And we do that now for every functional in the ensemble that we have in the BEEF ensemble of these fitted functional. And so we have an uncertainty now that comes in from the Gaussian process and from the underlying ensemble, and can combine, say, the whole uncertainty from the underlying electronic structure simulations to the point of, say, predicting adsorption energy or a barrier. And then we let it run. So first generation, it runs basically on a database of energetics that we already had sort of lying around. Then it suggests what should be the reaction path. And then it even says for every adsorbate and every barrier, well, which one of these is most uncertain because it's closest to a relevant barrier of one of the other reactions predicted in the machine learning method. Then you can go in and calculate those with DFT and figure out whether you were right. And then now having more DFT calculations, you fit the machine learning model again and run a new generation, right? And already here in sort of the 5th iteration, it figures out sort of the key step of the way that CO is being split. And in the 9th generation, it has converged to what it believes is the most relevant reaction path at this confidence level of choosing reaction paths. And so here for the case of syngas conversion to C2 species, or where you end up with alcohol over a rhodium surface, you're still doing a relatively big fraction of 10 to 15% of all the different species you're calculating by DFT. But if this was a syngas conversion and you're going to C20, you would be calculating an infinitesimally small fraction of the total number of structures that you'd normally be calculating. So the idea is that sort of fitting these surrogate models on the side can speed up your simulations tremendously by focusing your expensive DFT calculations on exactly where it needs to be, right? And I think that in terms of AiiDA, it would be interesting to, now that you have sort of the ability to save all these details about every single calculation you're doing and fitting these machine learning models along the way, now using those in fingerprints and setting up sort of a machine learning infrastructure in AiiDA so that you can make models for anything you want to do is a very natural next step and would allow you to sort of focus your DFT calculations on the most important things to be calculated next if you want to achieve a certain goal. For example, finding a better metal to do this and that, or etc. Right? Another example of this surrogate modeling approach is, for example, if we want to attack the problem of structure. So that is, under reaction conditions, we have the problem that our catalyst perhaps doesn't have the structure or the ordering of the elements that we are expecting it to have when we're doing our DFT calculation, right? Finding the correct structure and ordering can be a tremendous problem. And so let's take just sort of a simple example here. For example, if you're looking at bimetallic systems and you have sort of two different elements, then you typically have sort of here the stability varies you have a convex hull that looks something like this, and the activity of such clusters can change quite drastically as you change the composition or the way that these two different elements are ordered among each other in the cluster, right? And so now a problem is that there are very many different ways that you can make sort of clusters with a certain number of atoms, right? They can have different structures, but also if you just fix the structure, just the way to sort of organize two different elements on this lattice that is given a priori is a huge problem. Do they end up having sort of this ordering or that ordering? And trying to figure that out in general can be a quite demanding DFT task. For example here, if you have clusters with 147 atoms in a cluster, and you're just looking for the number of ways that you can arrange these two different elements, if you're sort of looking at an intermediate cluster here with half and half composition, there's maybe 10 to the 42 different ways of organizing these elements, right? And that's something you certainly don't want to search out explicitly by density functional theory, because you wouldn't get the results in this lifetime. Now, sort of, it's not an unsolvable problem, though, and I think we've really been surprised by how easy it actually is to solve. And I'll sort of go through the process that we went through. We use these genetic algorithms where you start out with some sort of random population of some random assignment of where these elements sits, right? And then you perform sort of crossover and mutation simulating sort of how the Darwinian evolution develops a population of species, and then you check whether they're fit, and if they're fit enough, then you sort of say, okay, this is maybe something that we should check in more detail. Now, here's, if you have these clusters with 147 atoms, and it's gold and platinum in this case, the stability or the convex hull of stability as a function of these different compositions looks something like this in the end. But you don't know that to begin with, because that really requires you to know sort of exactly how has it ordered for every composition, right? And so just for sort of one composition here in the middle, there's maybe 10 to the 42 different ways of ordering it, but you sort of have to do that for all compositions here in order to know your result. Now, you could sort of hope that if you just threw a genetic algorithm after it, and it sort of allows, during the crossover and mutation, to change the composition of what you have of the two different metals, that it would search out the correct composition for all the different, or the correct ordering for all the different compositions here. But the problem is that there are some that are more stable than others, and those that are more stable ends up being sort of sampled much more than the others. And you also have the problem that it sort of has a tendency to converge into sort of looking in one regime where it finds some very good solutions early. And so here's a result of just sort of throwing a GA after all the different compositions at the same time and hoping that something reasonable will come out. It doesn't really lead to a good result. And so sort of our order 0 method for solving the problem would be to make a genetic algorithm for each composition here and let it run until convergence, and that's how you get this out. Unfortunately, that ends up taking 500,000 electronic structure simulations. This was done with effective medium theory, so it's actually not a big deal. But if you wanted to do this accurately so that it's actually sort of something you could use, you would have to do it with density functional theory, and then 500,000 simulations would be too much for you to really carry it out, unless you really had a lot of computer power available. It's sort of barely on the limit of what would be possible today. So it would cost approximately, we've estimated, some 95 million CPU hours. It turns out that one can actually address this problem by using this genetic algorithm to search out all compositions at the same time. And the key is to change the fitness function from just looking for stability, is sort of different compositions with different stabilities. And instead of just sort of throwing the stability in there, you just rank the stability. So for each composition you look at, you say, what is my best stability, what is my second best stability, etc. And then using this as the fitness function, you have sort of made all compositions equivalent for the genetic algorithm, and it'll tend to search them out systematically again. And this reduces the number of electronic structure simulations you need by a factor of about 16. So you only need about 30,000. Now, that sort of got us more ambitious, and we figured out that it's very difficult to test these clusters whether you're actually sort of doing different things that are symmetrically equivalent. But you can sort of try that in various ways. And we came up with some descriptors, some descriptors that sort of figures out how many do you have of various types of nearest neighbors. And now, using that, you can sort of go in and see, oh, I think that this cluster here was actually the same one as I had calculated over here, so I probably don't need to do it again. That actually ends up taking a lot of time. And so it reduces the number of electronic structure simulation by about a factor of 2. So we only need 16,000 now, but for EMT simulations, it would probably be simpler just to carry out the 30,000 than to actually screen this. But what it did was that we now had something that begins to look like a fingerprint that you can do machine learning on, right? And it did reduce the number of electronic structure simulations a little bit. But the idea then came up to, why not fit a Gaussian process on this fingerprint, now that we have sort of a simple fingerprint that we know can sort of look at these different structures and figure out what they have in common. And we do that, and then it turns out that that machine learning model that we get out of that can calculate the stabilities with an error of only about 0.3 eV or something like this for the total formation energy of such a 147 atom cluster. And so getting a bit more ambitious, we sort of made other fingerprints, some that include the distance here from the center of mass of the different types of atoms, etc. And so it has some more dimensions, and it does perform sort of marginally better. It's actually not enough better that it really is worth putting a lot of effort into making a more complex fingerprint. And we took also one method that is used a lot these days from Matthias Rupp and Alex Sachenko and Anatole van Lilienfeld, this Coulomb matrix approach to calculating a fingerprint for these clusters. And there we can sort of squeeze down the error even further. Now it should be said that this sort of is not a totally honest fingerprint, because it requires the distance between the atoms, and we only have those after we have done the electronic structure calculation. And so there's sort of good reason to try and base your fingerprints on, say, a more graph representation of your structure than sort of a Cartesian position representation of your structure, if you don't know the Cartesian positions before you're doing your simulations, right? But now, sort of using this machine learning method to veto, sort of throw out suggestions to put into the genetic algorithm along the way, you can avoid calculating structures that the machine learning method says are way too poor to be relevant. And that way you can reduce the total number of electronic structure simulations to about 3,000. And that sort of inspired us to be a little bit more ambitious in using the machine learning method. And we actually integrated it with the genetic algorithm so that for every time we've done a DFT calculation, you fit a new machine learning method, you use the machine learning method in a genetic algorithm, run it until convergence, and it has suggested which are the most stable ordering of all the clusters. And then you calculate your next one, fit the model again, and using that you can actually bring it down even further to sort of you see here as the number of generations in your nested genetic algorithm increases, this total number of candidates that you need to calculate becomes lower and lower. And in the end, and that's sort of quite surprising, in order to find this convex hull, you basically need to calculate something on the order of 3 to 4 different orderings of every different composition here, just in order to have the sort of the most stable structure that you can find, which is sort of about a factor of 1,000 less than what we started out with. So ultimately, you can now actually carry this out with density functional theory, and then check whether what does density functional theory says about the structural ordering of all these different candidates, without it costing sort of a drastic number of simulations. And I think that really suggests that when you now have a structure like AiiDA, where it's easy for you in principle to make machine learning models, you should always do it, right? You should always, for anything you want to calculate, for anything where you want to make lots of density functional theory calculations, instead of just making it blindly and making a lot, you want to fit a machine learning method to the calculations that you have, and use that to predict where is it you should go with your next simulation, so that you focus your CPU power on those materials that gives you the most insight, right? Well, sometimes you really want to map out a certain space. You want to map out the alloys, the binary alloys or something like this, right? But if you're searching for something that's really complex, there's a huge benefit in having, say, even a rough machine learning model ahead of time to predict where is it you want to spend your computer time for the next one. I'm done, so that's perfect. Thank you very much.